This is part 8 of the Module 4 lecture, and here we will talk about counting rules. All right, counting outcomes is very important, and these rules are useful to determine the number of outcomes in a sample space of an experiment or the number of outcomes in a compound event. And now, in turn, these counts are useful when calculating theoretical probabilities. Some of these rules will be useful in Chapter 5, and some of them may be useful in the future. And that's why I decided to cover them, at least briefly. All right, the very first tool that I like to talk to is the tree diagram, and this is very useful to enumerate the outcomes of a sample space. In this example, I'm showing you a two-step experiment, where in the first step we toss a coin, and then in the second step we roll a die. And we would like to see what are the elements of the sample space. So when you toss the coin, you have two choices, rolling a head or rolling a tail. If you roll a head, and then you have the 6 possibilities of the rolling the die. If you roll a tail, then you have the same possibilities of the rolling a die. So when you put this together, you can see that the sample space for this two-step experiment is the heads with 6 possible rolls and the tails with the 6 possible rolls. Again, this is pretty simple, so probably you didn't need a tree diagram to see that. But I'm illustrating how the tree diagram is useful to determine or enumerate each of the outcomes of the sample space. All right, let's look at another multi-step experiment. In this case, the Texas Department of Motor Vehicles wants to issue new license plates to roughly 35 million vehicles in the state next year. It is proposed that only numbers be used in groups of 7 to form the license plate. So the question is, will this approach generate enough unique license plate numbers to satisfy the expected demand of 35 million? So this problem is equivalent to a 7-step experiment because you have to select 7 numbers. For each number selection, you have 10 digits to select from 0 to 9. So if you wanted to create this tree diagram, then you will have 7 tiers, each one with 7 outcomes. So I think enumerating the possible numbers for each license plate will be not easy to do. You will need a lot of time, a big area to do it. So in this case, the tree diagram may not be a good choice. So in this case, then we rely on the counting rule. And then the counting rule states that for an n-step experiment, where the event E1 has n1 outcomes, n2 has n2 possible outcomes, n3 has n3 possible outcomes, all the way to event E sub n, and with n sub n outcomes, then the total number of outcomes for the overall experiment is equal to the product of the number of outcomes for each of the events in each of the steps. So the counting rule is very useful, but note that only gives us the number of possible outcomes, but it does not tell us what the actual outcomes are, like the tree diagram. All right, let's go back to the example of issuing license plates in Texas. So again, in this case, as we said, the Texas Department of Motor Vehicles wants to issue roughly 35 million new license plates to vehicles next year. Now, using the numbers 0 to 9 in groups of 7, will that produce enough license plate numbers? Well, let's find out using the counting rule. So we have 7 steps. The first step, we have 10 digits to select from. In the next step, we have another 9 digits to select from because we're allowing the repetition of numbers. For the third number, or the third step, we have another 10 digits to select from. And you could keep on going all the way until you get the 7th number. So because you have 7 choices at each of the steps, you actually have 10 to the 7 possibilities, which is 10 million possible arrangements of 7 numbers with repeated numbers. Well, this is not a good approach. This is not producing enough to satisfy the demand of 35 million new license plates. So a new proposal is to use 3 letters and 4 numbers and allow repetition. So in this case, again, we have a 7-step process, where in the first step we have 26 letters to select from. In the second step, we have 26 letters to select from. In the third step, the same 26 letters to select from. The next step, now we have 10 numbers to select from, and so on until we complete the 7 digits in the license plate. So you will see that you have 26 to the 3rd power times 10 to the 4th power, and this will give you 175,760,000 license plates. So this approach will generate enough license plate numbers. So the counting rule tells you how many license plates you can have. It doesn't tell you what numbers or what arrangements of the 3 letters and 4 numbers you will have for each license plate. Typically, you need a computer algorithm to do this. All right, but this example illustrates how the counting rule could be helpful to determine the total number of outcomes in an experiment. Now, sometimes we are interested in forming groups of objects of a given number of objects that are available. In that case, we like to find out how many groups we can form of that number of objects when you have so many objects to select from. There are 2 types of arrangements, permutations and combinations. Permutations result when the objects can be arranged in such a way that the order of the arrangement distinguishes one outcome from another. Whereas combination is where you arrange the objects and the order of the arrangement does not distinguish one outcome from another. Let's look at a couple of examples to illustrate this. All right, permutations. Well, before we get to the examples, let's talk about how we calculate the number of permutations. So this symbol P with sub n on the left and sub r on the right means this is the number of permutations of n objects in groups of R. And this is the ratio of this quantity called n factorial. The exclamation symbol means factorial divided by n minus r factorial. And the condition is that R cannot be bigger than n. And that makes sense. If you have only n objects to choose from, you cannot select more than what you have. All right, n factorial, which is written as n exclamation mark, means that you multiply all the integers from n, whatever number n is, all the way to 1. For example, if you're looking at 3 factorial, that means you will multiply 3 times 2 times 1, and that will be 6. The n minus r factorial means that you first calculate the difference between n and r, and then you compute the factorial of that result. Let's say that n is 5 and r is 2. Then the difference, 5 minus 2, is 3. So 3 factorial will be 3 times 2 times 1, and that will be equal to 6. If you happen to have the n and r is the same number, so that difference will be 0. And 0 factorial is by definition 1. So keep that in mind as we progress. All right, let's look at an example of permutations. Here we have a student advisory board that consists of 17 members. Then 3 members serve as a board's chair, secretary, and webmaster. Each member is equally likely to serve in any of these positions. So what is the probability of selecting at random the 3 members that currently hold each position? So you have 3 people serving right now, and if you were to do a random selection, what is the probability that you will select the same 3? All right, first of all, let's realize that this is a permutation. Why? Because if you assign individuals to a position in the order that they are selected, that implies that the selection of when you select individual 1, individual 2, and individual 3 is going to be different from individuals 3, 1, and 2. Because say 1 is assigned as the chair, 2 as the secretary, and 3 as the webmaster in that selection or in that sequence. But if the sequence is 3, 1, 2, then individual 3 will be the chair, then individual 1 will be the secretary, and individual 2 will be the masters. So clearly the sequences show different outcomes. So there are 17 board members to select from, so N is 17, and you're selecting 3 officials, so R is 3. So to calculate the number of permutations of 17 individuals into groups of 3 will be 17 factorial divided by 17 minus 3 factorial, which is 17 factorial divided by 14 factorial. If you expand these factorials, you will see that the numerator will be 17 times 16 times 15 times 14 times 13, all the way to 1. If you expand the factorial in the denominator, so with 14 times 13 times 12, and so on, all the way to 1. And you can see that this 14 cancels with that, this 13 cancels with that, and all these numbers cancel each other. So what you have at the end is just 17 times 16 times 15. If you multiply those, you get a total of 4,080 permutations. So the probability of selecting the same 3 board members, which is one arrangement of all the possible arrangements or permutations in this case, so the probability of selecting exactly the same 3 members is 1 out of 4,080. That is a probability of 0.0002. All right, this is an illustration when you can use permutations. Now, the combinations is the number of R objects that can be selected from N objects when the order of the sequence does not distinguish one outcome from the other. So in this case, the number of combinations of N objects in groups of R is N factorial, N minus R factorial, but now we divide by R factorial. So this eliminates all the extra counts where the sequences do not indicate a new outcome. All right, let's look at an example. So a State's Department of Transportation received 16 bids to develop a new section of an interstate highway. The state plans to hire 4 of the bidding companies. The question is how many different groups of 4 companies can be selected from the 16 bidding companies. So in here we have 16 companies to select from, so N is 16, and 4 are to be selected, so R is 4. So the order of selection is not important because if you select companies A, B, C, and D, or D, C, A, and B, that means you are selecting the same 4 companies for bidding on this project. So the order of the sequence is not important here. So what we need to calculate is the number of possible combinations. So in this case, we have in the numerator 16 factorial and the denominator 16 minus 4 factorial divided by 4 factorial. And then so that simplifies to this. And then you can simplify the numbers by expanding the 16 factorial all the way to the 12 factorial, then the 12 factorial, and expanding the 4 factorial here. So this 12 factorial cancels with this, so you multiply these 4 numbers and divide this for these 4 numbers, and that will give you 1,820 combinations. So again, these are simple examples, but I hope I'm illustrating the difference between permutations and combinations. So with this, we complete module 4. The assignment is divided into 2 parts. One part is for this week. That's what we cover at the very beginning of chapter 4, the modules 1 and 2, with very few simple questions. So you should be able to solve those pretty easily, I think. All right. So at this point, you should be able to explain the concepts of a probability experiment, interpret probability, list its properties, and explain how to calculate it. Explain what a complement of an event is, what joint events are, and what the union of events are. Explain what a contingency table and all the probabilities associated with a contingency table. Calculate the probability of a complement of an event. Differentiate between independent events and mutually exclusive events. Explain what a conditional probability is and how it's calculated. And you should be able to use the multiplication and addition rule to calculate probabilities of joint events or the union of events. And finally, you should be able to distinguish between the different techniques to calculate the number of outcomes of an experiment. All right, so we're finished with module 4, fairly long module. All right, thank you.